Okay, so we are connected. I was thinking to start it again after my lesson, but I just started eating a lot. So then I didn't get any time to again start. Actually, I got time, but I didn't start. So I was just eating and eating and eating stuff. Okay, so let's continue so that we can finish that another chapter today. It's gonna take some time to finish that chapter, but we are gonna do it. Okay. So, oh, I have a lot of windows open. Let me close it. Okay, here we go. So, where are we? Yeah, so we are going to do the relationship between the pointers and the arrays. I must tell you that we are on page number 73 right now, which is not bad. It's bad, but it's not. Okay, fine. So, we'll read the pointers and arrays from the top again. In C++, arrays and pointers are defined in such a way that a complete understanding of either topics requires that you understand the other. Arrays, for example, are implemented internally as pointers. True, because every element in an array is nothing but a pointer. The operations on pointers only make sense if you consider them in relation to an array. Thus, in order to give you the full picture of how arrays and pointers work, it is important to consider the two concepts together. To get a sense of the relationship, consider the simple array declaration double list 3, which reserves enough space for 3 values of type double. Assuming that a double is 8 bytes long, the memory diagram for the array would look like this. Because each of the elements in the array is an L value, it has an address that can be derived using the ampersand operator. For example, the expression ampersand L list square brackets L1 has the pointer value 1008 because the element list 1 is stored at that address. Moreover, the index value need not to be constant. The selection expression is an I value, L value, and it is therefore legal to write ampersand list square brackets I, which indicates the address of the ith element in the list, which is fine. Because the address of the ith element in the list depends on the value of the variable I, the C++ compiler cannot compute this address when compiling the program. To determine the address, the compiler generates instruction that takes the basic address of the array and then adds the value to I multiplied by the size of each array element in bytes. So basically, if the starting element's starting bit address is 1000, because let's say we are storing doubles, so every double takes 8 bytes size. Yes, I'm right. Yes. Okay, so every double takes 8 bytes size. So if the starting address of the first double is 1000, then the next double will come after 8 bytes, right? So we will do 1000 plus I multiplied 8, and I can be the first or the second element or the third element and so on, like that. If I is 2, for example, then we will do the calculation and we will get 1016 as the starting index, as the starting address of the element 2, second index element, I mean. Okay, the relationship between pointers and arrays. Among the unusual characteristics of C++, one of the most interesting is that the name of an array is treated as being synonymous with a pointer to the initial element in that array. This concept is most easily illustrated by example. Allocate space for an array of 5 integers which is assigned storage somewhere else. Okay, this is all easy. The name int list represents an array but can also be used directly as a pointer value. When it is used as a pointer, int list is defined to be the address of the initial element in the array. True. Given any array name, you can assign its address directly to any pointer variable. So you can say ampersand arr0. The most common example of this equivalence occurs when an array is passed from one function to another. For example, suppose that you make the function call it's so hot. The air conditioner is not even on. Okay, fine. So when we are passing the array into it, the sum integer array function would work exactly the same way if the prototype had been written as. Oh, okay, that's what they're talking about. If you want to pass an array into a function, you can either pass it as int array square brackets. That's one thing, that's one way of passing it. Another way is int star array. In this case, the first argument is declared as a pointer, but the effect is just the same as in the preceding implementation, which declared this parameter as an array. The address of the first element in the int list is copied into the formal parameter array and manipulated using pointer arithmetic. Inside the machine, the declarations are equivalent and the same operations can be applied in the either case. As a general rule, you would declare parameters in the way that reflects their use. If you intend to use a parameter as an array and select elements from it, you should declare that parameter as an array. If you intend to use the parameter as a pointer and dereference it, you should declare it as a pointer. The crucial difference between arrays and pointers in C++ comes into play when variables are originally declared, not when those variables are passed as parameters. The fundamental distinction between the declaration is this. Is one of the memory location. The first declaration reserves 5 consecutive words of memory capable of holding the array elements. The second declaration reserves only a single word which is large enough to hold a machine address. The implication of this difference is extremely important to you as a programmer. If you declare an array, you have storage to work with. If you declare a pointer variable, that variable is not associated with any other storage until you initialize it. Okay. Given your current level of understanding, the only way to use a pointer as an array is to initialize the pointer by assigning the base address of the array to the pointer variable. If after making the preceding declarations you were to write p equals to array, the pointer variable p would then point to the same address used for the array, and you could use the two names interchangeably now. The technique of setting a pointer to the address of an existing array is rather limited. After all, if you already have an array name, you might as well use it. Assigning that name to a pointer does not really do you any good. The real advantage of using a pointer as an array comes from the fact that you can initialize that pointer to new memory that has not previously been allocated, which allows you to create new arrays as the program runs. This important programming technique is described in the section called dynamic allocation. And what did I just say? I'm gonna read that again. The technique of setting a pointer to the address of an existing array is rather limited. After all, if you already have an array name, you might as well use it. Assigning that name to a pointer does not really do any good to you. The real advantage of using a pointer as an array comes from the fact that you initialize that pointer to the new memory that has not previously been allocated, which allows you to create new arrays as the program runs. Okay. Okay. So if you have an array and its memory is now exhausted, you can assign that initial pointer to another array and kind of join them somehow. We don't know how to do that yet because we haven't seen it in the dynamic allocation. We'll see it when we come to that topic. We have another topic called records. Okay. To understand the idea of a record, imagine for a moment that you're in charge of the payroll system for a small company. You need to keep track of various pieces of information about each employee. For example, in order to print a paycheck, you need to know the employee name, job title, social security number, salary, withholding status, and perhaps some additional data as well. These pieces of information taken together form the employee's data record. What do employee records look like? It is often easiest to think of records as entries in a table. For example, consider the case of the small firm of Scrooge and Marley, portrayed in Charles Dickens' A Christmas Carol, as it might appear in this day of social security numbers and withholding allowances. The employee roster contains two records which might have the following values. Each record is broken up into individual components that provide a specific piece of information about the employee. Each of these components is usually called a field, although the term member is also used, particularly in the context of C++ programming. For example, given an employee record, you can talk about the name field or the salary field. Each of the fields is associated with a type, which may be different for different fields. The name, the title fields are string. The salary field might be represented as a floating point number, and the number of withholding exemptions is presumably an integer. The social security number could be represented as either integer or string, because social security numbers are too big to fit into the limits imposed on integers by many systems. They are represented here as strings. Even though a record is made up of individual fields, it must have a meaning as a coherent whole. In the example of the employer roster, the fields in the first line of the table represents a logically consistent set of data referring to the Ebenezer screws. Those in the second line refers to the Bob Cratchit. The conceptual integrity of each record suggests that the data for that employee should be collected into a compound data structure. Moreover, since the individual fields making up that structure are of different types, arrays are not suited to the task. In cases such as this, you need to define the set of the data for each employee as a record. And what do we mean by a record? Defining a new structure type. So we don't have a structure which is going to fit this kind of data in it. So we are going to create a new structure using struct. Defining a new structure type. Before you declare any variables, you must define a new structure type. The type definition specifies what fields make up the record, what the name of those fields are, and what type of information each field contains. This structure type defines a model for all objects that have the new type but does not by itself reserve any storage. Declare variables of the new type. Once you have defined the new type, you can then declare variables of that type so that you can store actual data. The general form for defining look like this, but if you are making a employee record structure, then you can say struct employee record, and inside it you can say string name semicolon string title semicolon string social security name number double salary int withholding, like that. This definition provides a template for all objects that have this new type employee record T. Each such object will have 5 fields, starting with the name field with a string and going till the withholding field, which is an int. Declaring structure variables. Now that you have defined a new type, the next step is to declare variables of that type. How do you do that? You just write the name of your struct and then name of your variable of that struct, and you got a box named as that, and that box will contain 5 variables to it, so you need to assign the values of that. To refer the values of each variables, you can say employee rec dot title, so you can use dot notation. Selecting a field using the dot operator is called record selection. Initializing records. As with any other type of variable, one second, hello, huh, स्टेटमेंट में भेज देंगे मतलब ठीक है ओके Okay, let's get back. So, initializing records, we did the record selection, and then to initialize all the values in the record, you can use mprec.name equals this, and then like that, you can initialize all of them. Or you can initialize all of them together instead of doing dot notation. You can also treat that as an array of values. So you can say employee record T, that's the struct name, and then you put a space and you put the name of that struct and manager, let's say, and then you can put equals and put curly brackets and you put five values inside it. That's also how you can initialize it. Pointers to records. Although small records are sometimes used directly in C++, variables that hold structured data in C++ are often declared to be pointers to records rather than the records themselves. A pointer to a record is usually smaller and more easily manipulated than a record itself. So, suppose for an example that you want to declare a variable that points to employee records. So, you can do it like the name of the struct, then star, and then the pointer name. So, M pointer is a pointer to an object of type employee record struct. When you make this declaration, space is reserved only for the pointer itself. Before using M pointer, you still need to provide the actual storage for the fields in the complete record. The best approach is to allocate space for a new record as described in the next section on dynamic allocation. For the moment, let's assume that the earlier declaration is still around. That means you can make employee pointer to the employee record by writing this. You can say empptr equals to ampersand emp record. Makes sense. Starting from empptr, how can you refer to the individual field in the underlying record? So, yeah, when you are assigning a pointer to a record, you can use ampersand to assign it because you are assigning an address. But when you are trying to access the values inside it, you can say star employee pointer dot salary, because you need to use star first so that you get the value. After you get the whole array of values, which contains 5 values, from that you can do dot salary. Okay. Oh, so make sure that you first do employee pointer dot salary. So the selection operator will come first. Then you will do the dereferencing of the whole thing. You will do the selection operator. So you will do emp pointer because it's pointing to the whole thing. From that you will get the pointer to just the salary by doing dot, and then you will dereference it using star. So you will dereference the whole thing. So put it in the parenthesis, that's better. Okay, makes sense. The letter form has the desired effect but is too much cumbersome for everyday use. Pointers to structures are used all the time. For C++ defines the operator arrow, which combines the operations of dereference and selection into a single operation. Thus, the conventional way to refer the salary in the record to which employee pointer points to is to write emp pointer arrow salary. That's also a possibility. Otherwise, you need to say employee pointer dot salary, put it in a parenthesis, and then do the dereferencing of it, which is star. Actually, both of them make sense, so it's good. Okay, let me write one little thing. It's the date today, it's 11th of June, and it's what, Wednesday today? Yeah. Okay, great. Now let's move to the dynamic allocation. Up to this point in the text, you have seen two mechanisms for assigning memory to the variables. When you declare a global variable, the compiler allocates memory space for that variable, which persists through the entire program. When you declare a global variable, the compiler allocates memory space for that variable, which persists throughout the entire program. This style of allocation is called static allocation because the variables are assigned to fixed locations in the memory. Wait a minute. What do you mean? Up to this point in the text, you have seen two mechanisms for assigning memory to the variables. When you declare a global variable, the computer allocates memory space for that variable, which persists through the entire program. This style of allocation is called static allocation because the variable is assigned to the fixed location in the memory. Oh, so when you make a global variable, you assign a fixed location to that variable in the memory, and that's never going to change throughout the whole program. And that's called static allocation. When you declare a local variable inside a function, the space for that variable is allocated on the system stack. Calling the function assigns memory to the variable. That memory is freed when the function returns. This style of allocation is called automatic allocation. But there is also a third way of allocating memory that persists you to acquire new memory when you need it and free it explicitly when it is no longer needed. And the process of acquiring new storage while the program is running is called dynamic allocation. So there are three types of allocation. The global variable does the static allocation because you make it once and it persists throughout the whole program. Second type of allocation is the automatic allocation. In the automatic allocation, it's because it's on the functions which we use because it gets freed up and it gets created by its own, so it's automatic allocation. But the dynamic allocation means you can make it when you need. You can make a new memory when you need, and you can delete it or free it up when you're done using it. So that's called dynamic allocation. When a program is loaded into memory, it usually occupies only a fraction of the available storage. In most systems, you can allocate some of the unused storage to the program whenever it needs more memory. For example, if you need space for a new array while the program is running, you can reserve part of the unallocated memory, leaving the rest for the subsequent allocations. The pool of unallocated memory available to a program is called a heap. In C++, you can use the new operator to allocate memory from a heap. In its simplest form, the new operator takes a type and allocates space for a variable of that type located in the heap. For example, if you want to allocate an integer in the heap, you call int star ip equals new int. This is the syntax of allocating a new integer memory in the integer memory. Yeah. The call to the new operator will return the address of the storage location in the heap that has been set aside to hold an integer. And because it is returning the address, that's why we are storing it in the the asterisk variable. So it's the pointer to that location. The new int returns you the storage address. That's why we are storing it into the star id. The new operator can also be used to allocate variables of compound type. To allocate a compound type, you also do the exact same thing. You just put that compound type struct name instead of the int or float. The new operator is a variant that is used to allocate an array in the heap, new square bracket. So basically, when you are doing a new integer, you just do new int. But if you're doing a new integer array, you do new int square brackets and then you put the size of it. And the same thing for the hybrid data type or the data type which you made. For that also you will say, why is it so weird? Okay. For that also you will say the same thing. You will do new employee record and then you put square brackets 1000. So you create thousands of that. So the address returned by a new square bracket is the base address of a contiguous piece of memory large enough for the entire array. You can index into dynamic array using ordinary subscript notation just as you would do for a static array. Coping with memory limitations. Although they are getting larger all the time, computer memory systems are finite in size. As a result, the heap will eventually run out of space. When this occurs, the new operator will eventually be unable to allocate a block of the requested size. The failure to fulfill an allocation request is such a serious error that the default behavior is for the program to immediately halt. One way to help ensure that you don't run out of memory is to free any storage you have allocated when you are finished using it. C++ applies the operator delete, which takes a pointer previously allocated by new and returns the memory associated with that pointer to the heap. One way to help ensure that you don't run out of the memory is to free any storage you have allocated when you are finished using it. C++ applies the operator delete, which takes a pointer previously allocated by new and returns the memory associated with that pointer to the heap back. Okay, basically giving the memory back to the heap. If, for example, you determine that you are completely finished using the storage allocated for PTR, you can free that storage for later use by calling delete PTR. Here you don't need to put ampersand or an asterisk. You can just put the pointer name and you will delete it. Okay, and if you want to delete an array which you made before, you can say delete square brackets and then the pointer name. Knowing when to free a piece of memory is not always an easy task, particularly as programs become large. If several parts of the program share some data structure that has been allocated in the heap, it will not be possible for any single part to recognize that the memory can be freed. Given the size of the memories today, however, you can often allocate whatever memory you need without even bothering to free it again. The problem of limited memory typically becomes critical only when you design an application that needs to run for a long period of time, such as the operating system on which all the other facilities of the system depend. In these applications, it is important to free memory when you no longer need it. Some languages, including Java, support a system for dynamic allocation that actively goes through memory to see what parts of it are in use, freeing any storage that is no longer needed. This strategy is called garbage collection. Garbage collecting allocators exist for C++, and it is likely that their use will increase in coming years, particularly as people become more familiar with their advantages. If it does, the policy of ignoring reallocation will become reasonable even in long-running applications because you can rely on the garbage collector to perform the deallocation operations automatically. For the most part, this text assumes that your applications fall into the class of problems for which allocating memory whenever you need it is a workable strategy. This assumption will simplify your life considerably and make it easier for you to concentrate on algorithmic details. Dynamic arrays. From a conceptual perspective, an assignment of the form CB equals new character square brackets 10 creates the following configuration in memory. Makes sense. I need to put everything, all the utensils, and also get some water. So let me get back to that. So we are actually at the point where we are going to do dynamic arrays now. So in this case, we don't make the arrays by just saying int and then the array name and then equal square brackets 10 equals curly brackets and not even putting the size. It will still count all the elements in the curly brackets and it will still make it that size. But in this case, we are going to create the dynamic arrays. From a conceptual perspective, an assignment of the form creates the following configuration in the memory. Okay, so we can do cp equals new char square brackets 10. Now remember, we are using new here, and new creates a memory in the heap and gives you the address of that memory. So the cp is going to be a pointer to that memory location of 10 consecutive bytes that have been allocated in the heap. Because pointers and arrays are freely interchangeable in C++, the variable now acts exactly as if it had been declared as an array of 10 characters. Okay. Array that you allocate on the heap and reference using a pointer variable are called dynamic arrays and plays a significant role in modern programming. The principal differences between declared arrays and dynamic arrays are that the memory associated with a declared array is allocated automatically as a part of the declaration process. When the frame for the function declaring the array is created, all the elements of that array are allocated as part of the frame. In the case of a dynamic array, the actual memory is not allocated until you invoke the new operator. True. Yeah, you need the new operator, otherwise it will not assign the memory to you. The size of the declared array must be constant in the program. In contrast, because its memory comes from the heap, a dynamic array can be of any size. Moreover, you can adjust the size for dynamic array according to the amount of data. If you know you need an array with precisely n elements, you can reserve just the right amount of the storage. You can allocate a dynamic array using the new operator. For example, if you wanted to initialize the variable dArray to a dynamic array of n values of type double, you would declare dArray using the line. Okay, so you declare it first and then you assign it to some number of bytes which you want to create. Let's say I want to do double star dArray. Then you will do dArray equals new double square brackets n. Because new is going to allocate a memory in the heap, and how many memory do we want? We want n memory locations, and how big each of these memory locations should be. So that depends on the data type we are mentioning in it, and because it's going to return you the address of that, that's why you need to put it in this asterisk dArray, not a normal dArray. Okay, dynamic records can also be there because this was dynamic arrays. Dynamic memory location allocation is just as useful for records as it is for arrays. If you declare a pointer to a record, you can allocate memory to store the actual data in the record by calling new. For example, if the type employee record T is defined as this, then you can assign the space for a newly allocated record like this and this, okay, and like this. Yeah, that's making all sense. Okay, I'm on the summary of this chapter, and it was a really nice chapter because all of the concepts were related to pointers and arrays and records. It was really nice. Summary: it actually revised all the things related to C++ which sound difficult for the first time. It revised everything, so it's a really nice chapter, I would say. In this chapter, you have learned how to use the data structure definition capabilities of C++ to create data types. The data structures presented in this chapter are pointers, arrays, and records, form the foundation for abstract data types. The principal advantages of these structures is that you can use them to represent data in a way that reflects the real world structure of an application. Moreover, by combining pointers, arrays, records in the right way, you can create hierarchical structures that allows you to manage data complexity in much the same way that decomposing a large program into separate functions allows you to manage algorithmic complexity. Important points in this chapter include C++ allows you to define new atomic types by listing the elements that comprise the domain of the type. Such types are called enumeration types. And are part of a more general class called scalar types that also includes characters and integers. Data values inside a computer are represented as collection of bits that are organized as large structures called bytes and words. Every byte in the memory is associated with a numeric address that can be used to refer the data contained in that location. Addresses of the data in the memory are themselves data values and can be manipulated as such by the program. A data value that is the address of some other piece of the data is called pointer. The pointer variables are declared in C++ by writing an asterisk in front of the name in its declaration line. The fundamental operations on pointers are ampersand and asterisk, which indicate the address of the stored value and the value stored at a particular address, respectively. There is a special pointer called null, which is used to indicate that a pointer does not refer to anything. An array is an ordered, homogeneous collection of data values composed of elements indicated by an index number. In C++, index numbers in an array always begin with 0. Arrays are declared by specifying a constant size in square brackets after the name of the array. The size specified in the declaration is called the allocated size of the array, and it's typically larger than the effective size, which is the number of the elements usually in use. Oh, true. When the array is passed as a parameter, the elements of the array are not copied. Instead, the function is given the address of the actual array. As a result, if the function changes the value of the elements of the array, those changes will be visible to the caller, which is working with the same array. A record is a heterogeneous collection of the data values that form a logically consistent unit. The storage for arrays and records can be allocated dynamically from a pool of unused memory called a heap. The standard operators new and new square brackets are used to allocate records and the dynamic arrays respectively. Review questions. Define each of the following term: pointer, array, and record. Pointer is it's to store the address of the memory location which stores a value. Array is a continuous array is a pointer to the continuous group of continuously allocated group of elements of homogeneous elements. Yeah. Record is a pointer to the address of a group of heterogeneous elements. Yeah. What type definition would you use to define a new enumeration type? Polygon T of the following elements. How would you change the definition so that internal representation of a number of sides for that polygon? Ah. I see. I remember this actually. Okay, these are all the questions. I think we can use all of these questions. I can use this in the lesson. It's pretty good. It's pretty good. So I'm done with this chapter, and I'm gonna move to the third chapter. How long this live stream? going on? How long it's been? It's 41 minutes since it started. So let's keep on going, and let me just do one thing before we continue. One second. लो इसको ही पूजा कराओ, इसको परेशानी बनाओ.
दिमाली को मत पूजा करें फिर ये पूजा करेगा.
Okay, so we are going to do the chapter number 3, libraries and interfaces. In modern programming, it is impossible to write interesting programs without calling library functions. Yeah, that's true, because we can't write everything from the scratch, so we need to use some library functions. In fact, as the science of programming advances, programmers depend more and more on the library functions. Because if a programmer already created something, why not just use it? Why do we create our own? That will be just a waste of time, right? Today, it is not at all unusual for 90% or more of a program to consist of a library code, with only a few parts specifically tailored for a particular application. True, even if you're making a program on Django, you're using most of the things which are already there in Django. You're not creating anything, so you're just using it. And I've seen people using the QR code library and then saying that I made a code which scans the QR code and tells what's inside it. But they just use a single line of code, and that's just the library itself, which is weird. As a programmer, you must understand not only how to write new code, but also how to avoid doing so by making appropriate use of the existing libraries. The main purpose of this chapter is to encourage you to think about libraries in a way that emphasizes the distinction between the library itself and other programs that make use of it, which are called its clients. To do so, the chapter focuses on the boundary between a library and its clients, which is called the interface. The interface provides a channel of communication but also acts as a barrier that prevents complex details on one side from affecting the other. Interfaces are central to a modern treatment of libraries, and it is important, even if you have done a lot of programming, for you to understand libraries from this perspective. So you need to understand that the program which is using the library, that's called client, and the program uh, which we are using, it's called library, and the interface is the bridge between them so that we can use them regardless of looking at the difficulties of the library. So we should just focus on how to use it, not on the difficulties. So let's dive into the interface, the concept of an interface. In English, the word interface means a common boundary between two distinct entities. The surface of a pond, for example, is the interface between the water and the air. True. In programming, an interface constitutes of a conceptual boundary rather than a physical one. An interface is the boundary between the implementation of the library and its clients. The purpose of the interface is to provide each client with the information it needs to use the library without revealing the details required by the implementation. Yeah, why do we need to go into the details of that library? We just want to use it, right? So interface is coming in between so that it can tell client how to use the important information it needs but without revealing the details which are not required. Okay. Thus, it is important to think of an interface not only as a channel for communication between client and implementation, but also as a barrier that keeps them separated, as illustrated by the following diagram. Client and the implementation. The interface is coming in between. They can talk to each other, but they cannot pass from it, so they can't see each other. By mediating the communication between the two sides, an interface reduces the conceptual complexity of the programming process by ensuring that details that lie on one side of the interface boundaries do not escape to complicate the code on the other side. Interfaces and implementations. In computer science, an interface is a conceptual entity. It consists of an understanding between the programmer who implements a library and the programmer who uses it, spelling out the information that is required by both sides. When you write a C++ program, however, you must have some way to represent the conceptual interface as part of the actual program. In C++, an interface is represented by a header file, which traditionally has the same name as the file that implements it, with the C++ extension replaced by .h. Oh, okay. So if you want to make an interface instead of a normal C++ program, you make the extension as .h instead of the .cpp extension. Hmm. As an example, suppose that you have created a collection of functions that you want to make available to the clients as a library. To do so, you need to create two files as an interface that you might call mylib.h and the corresponding implementation mylib.cpp. So there will be two files. One is called the interface and one is called the implementation, which has the actual code. So the mylib.h and the mylib.cpp. We don't know what's inside the mylib.h yet. We will learn about it later. The code for each of your functions goes in the mylib.cpp implementation file. The code is inside the cpp extension. The mylib.h interface contains only the function prototypes. Okay, which contains the information the compiler needs to interpret any calls to these functions. Putting the prototypes in the interface makes them available to clients and is called exporting those functions. So in the .cpp we have the actual functions, but in the .h file we just have the prototypes of all the functions. So basically no body of the function is there. So we have, if we are going to use any library in our code, we are having the access to the prototype of those functions. So we have the access of the .h file, we don't have the access of the .cpp file, so that we can't see what's written inside the functions, because that's the code which other person wrote, and it's something which we should not see, right? Because it took a lot of time for him to write or her to write. So putting the prototypes in the interface makes them available to the clients and is called exporting those functions. Although function prototypes are the most common components of an interface can export other definitions as well. In particular, interfaces often export data types and constants. A single definition exported by the interface is called interface entry. So the most common component is functions. function prototypes. The most common components of an interface is function prototypes, but it can export more things as well, which can be a data type or a constant. A single definition exported by an interface is called an interface entry. Once you have written the interface and the implementation for a library, you or some other programmer with whom you are collaborating can then write separate source files that act as clients of the mylib.h interface. The relationship between the files representing the client, interface, and implementation is illustrated in the following diagram. So we have client.cpp, which is a client of a library interface, is a source file that makes use of the definition exported by the library. Mylib.h is the file with which the client.cpp is going to interact. The interface contains only the information about the library that its client needs to know. And then the mylib.h is going to contact with the mylib.cpp, and the mylib.cpp actually contains the code to make the library work, the details of which are not of interest to the client. The distinction between the abstract concept of an interface and the header file that represents it may at first seem subtle. In many ways, the distinction is the same as between an algorithm and a program that implements it. The algorithm is an abstract strategy. The program is a concrete realization of that algorithm. Similarly, in C++, header files provide a concrete realization of an interface. Okay? Now we have packages and abstractions. So the same distinction between a general concept and its programming manifestation also comes up in the definition of two other terms that are often used in discussions of interfaces. In computer science, you will often hear the term package a lot, used to describe the software that defines a library. शोर आ रहा है तुम्हारा In computer science, you will often hear the term package used to describe the software that defines a library. A software that defines a library. What do you mean? If you're assigned to develop a library, part of your job consists of producing a H file to serve as the library interface and a corresponding CPP file that provides the underlying implementation. Those files constitute the package. Oh, okay. So the package is just a folder which contains these two files. One is the .h and one is the same name file with the .cpp extension. Yeah, makes sense. One is the interface of the library and one is the implementation of the library. To get a full understanding of a library, however, you must look beyond the software. Libraries embody a specific conceptual approach that transcends the package itself. The conceptual basis of a library is called an abstraction. The relationship between an abstraction and a package is best illustrated by an example. The programs in the first two chapters of this text use the insertion operator and the cout stream from the iStream interface for all the output operations. For input operations, however, those programs use functions exported by the simpio.h interface, such as, wait a minute, I need to read this slowly, this part. I'm gonna eat and read in my mind. So basically, the sympio.h is an interface of the sympio library, and the IO stream is also itself not a library, it's an interface of the IO stream library which has the input and output functionalities. Okay, let me just finish it. I'm eating a lot of sweet things these days, which is really bad. That's why I keep on sipping the water just to make myself feel that I'm not eating that much sweet things. So now we are at a point which has a topic called Principles of Good Interface Design. The programming is hard because programs reflect the complexity of the problems they solve. As long as we use computers to solve problems of ever increasing sophistication, the process of programming will need to keep becoming more sophisticated as well. Writing a program to solve a large or a difficult problem forces you to manage an enormous amount of complexity. There are algorithms to design, special cases to consider, user requirements to meet, and innumerable details to get right. To make programming manageable, you must reduce the complexity of the programming process as much as possible. One of the primary purposes of defining new functions is to reduce complexity by dividing up the entire program into more manageable pieces. Interfaces offer a similar reduction in programming complexity but at a higher level of detail. A function gives its caller access to a set of steps that together implement a single operation. An interface gives its client access to a set of functions that together implement a programming abstraction. The extent to which the interface simplifies the programming process. However, it depends largely on how well it is designed. Okay, so an interface gives its clients access to a set of functions that together implement a programming abstraction. Why are we calling it an abstraction? Because it doesn't have its own implementation in the interface. It's just some abstract types, abstract functions, because it's just the prototype of the functions. That's why we say that it is implementing an abstraction. To design an effective interface, you must balance several criteria. In general, you should try to develop interfaces that are unified, simple, sufficient, general, and stable. And let's read through it. Let me just see how many. Four. Okay. Yeah. So, to design an effective interface, you must balance several criteria. In general, you should try to develop interfaces that are unified. A single interface should define a consistent abstraction with a clear unifying theme. If a function does not fit within that theme, it should be defined in a separate interface. Okay. Simple, to the extent that the underlying implementation of is itself complex, the interface must hide as much of that complexity from the client as possible. Sufficient. When clients use an abstraction, the interface must provide sufficient functionality to meet their needs. If some critical operation is missing from an interface, clients may decide to abandon it and develop their own, more powerful abstraction. As important as simplicity is, the designer must avoid simplifying an interface to the point that it becomes useless. General. A well designed interface should be flexible enough to meet the needs of the many different clients. An interface that performs a narrowly defined set of operations for one client is not as useful as one that can be used in many different situations. Stable. The functions defined in an interface should continue to have precisely the same structure and effect even if their underlying implementation changes. Making changes in the behavior of an interface forces clients to change their programs, which compromises the value of the interfaces. Oh, okay, so once you create an interface, see, you should not change that .h file. You can change what is inside those functions, but the prototypes of the functions should not change. The name of the function, the inputs it's taking, that should not change. Because it is important to maintain stable interfaces, the designer of an interface must exercise special care to get it right. As more and more clients start to depend on a particular interface, the cost of changing that interface increases. In fact, it is quite common to discover interfaces that cannot be changed at all, even if they have serious design flaws. Certain functions in the standard libraries, for example, exhibit behaviors that are widely considered flaws by the C++ programming community. Even so, it is impossible to change the design of these functions because too many clients depend on the current behavior. Some interface changes, however, are more drastic than others. For example, adding an entirely new function to an interface is usually a relatively straightforward process since no clients already depend on that function. Changing an interface in a way that requires no changes to the existing programs is called extending the interface. If you find that you need to make evolutionary changes over the lifetime of an interface, it is usually best to make those changes by extension. Extending the interface is still fine, but changing the same prototypes which are already there, not a good thing to do because a lot of clients are dependent on that now. A random number interface. The easiest way to illustrate the structure of an interface is to provide a simple example. The libraries for this book and its C based predecessor include an interface called random.h that makes it easier for client programs to, to simulate random processes like flipping a coin or rolling a dice. Getting a computer, which ordinarily operates deterministically in the sense that running the same program with the same input always produces the same result. To behave in a random way involves a certain amount of complexity. For the benefit of client programmers, you want to hide this complexity behind an interface so that the client has access to the capabilities it needs without having to confront the complexity of the complete implementation. The structure of the random.h interface. Random.h interface, which exports the functions random integer, random real, random chance, randomize. For each of these functions, the interface contains a one line prototype along with a comment that describes the purpose of the function from the perspective of the client. As is typical for the interfaces defined in this text, comments comprise most of the interfaces and provides all the information clients need. If the comments in an interface are well designed, clients should be able to rely on them without having to read the underlying implementation. After the initial comment that describes the interface, the random.h interface includes a somewhat cryptic set of lines that is part of conventional syntax for interface. The lines in and def random-h define random-h operate in conjunction with the last line of the interface, which is and if. These three lines are often referred as interface boilerplate. When you design your own interfaces, you should be sure to include similar boilerplate lines, substituting the name of your own interface for the name random in this example. The purpose of the interface boilerplate is to prevent the compiler from reading the same interface many times during a single compilation. Oh. Hmm. The line if endef random edge causes the compiler to skip any text up to the endif line if the symbol random edge has been previously defined. When the compiler reads this interface for the first time, random edge is undefined, which means that the compiler goes ahead and reads the contents of the file. The compiler immediately thereafter encounters the definition define random edge. Hmm. The remainder of the interface consists of the function prototypes and their associated comments. The first prototype is for the function random integer low high and then so on like that. In mathematics, a range of real numbers that can be equal to the endpoint but not the other is called half open interval. Okay. On a number line, a half open interval is marked as open circle to show that the endpoint is excluded, like this. In text, the standard convention is to use the square bracket. Okay. The function this is used to simulate random events that occur in the same some fixed probability. To be consistent with the convention of statistics, a probability is represented as number between 0 and 1, where 0 means that the event never occurs and 1 means that it always does. The random chance function returns a Boolean value that is true with the probability p, so that the random chance 0.5 returns true 70% of the time. 75% of the time. You can use random chance to simulate flipping a coin as illustrated by the following function, which returns either heads or tails. The last chance in the random.h interface requires a little more explanation because computers are deterministic machines. Random numbers are usually computed by going through a deterministic calculation that nonetheless appears random to the user. Random numbers computed in a way are called pseudo-random numbers. If you take no special action, the computer always applies the same process to generate its sequence of random numbers, which means that the result will be the same every time the program is run. The purpose of the randomize function is to initialize an initial pseudo-random number generator so that each run of the program produces a different sequence, which is what you want if you are writing a program that plays a game. At first, it may seem hard to understand why a random number package should return the same values on each run. After all, deterministic behavior of this sort seems to defeat the whole purpose of the package. There is, however, a good reason behind this behavior. Programs that behave deterministically are easier to debug. To illustrate this fact, suppose you have just written a program to play an integrate game, such as Monopoly. As is always the case with the newly written programs, the odds are good that your program has a few bugs. In a complex program, bugs can be relatively obscure in the sense that they only occur in rare situations. Suppose you are playing the game and discover that the program is starting to behave in a bizarre way. As you begin to debug the program, it would be very convenient if you could regenerate the same state and take a closer look at what is going on. Unfortunately, if the program is running in a non-deterministic way, a second run of the program will behave differently from the first. Bugs that showed up the first time may not occur on the second pass. In general, it is extremely difficult to reproduce these conditions that cause a program to fail if the program is behaving in a truly random fashion. If, on the other hand, the program is operating deterministically, if it will do the same thing each time it is run. This behavior makes it possible for you to recreate the conditions where which the program occurred. When you write a program that works with the random numbers, it is usually best to leave out the call to randomize during the debugging phase. When the program seems to be working well, you can insert a call to randomize at the beginning of the main program to make the program change its behavior from one run to the next. Okay, that all make real sense. Constructing a client program. Okay, we'll see that after 2 minutes. Just gonna see something. Okay, okay, let me just try. Hmm. Okay, let's get back to it. Constructing a client program. Once you know what the interface looks like, you can immediately begin to code applications that use it. The interface provides all the information that any client needs to know. From the client's perspective, the important questions are what the functions in the library do and how to call them. The details of how they work are important only for the implementation. As a simple illustration of how clients can use the random number package, let's consider craps.cpp program, which stimulates the casino game of the craps because the program uses the random number library to simulate the rolling the dice. The craps.cpp file needs to include the random.h interface. Moreover, in order to ensure that the outcome is not the same every time, the program calls randomize at the beginning of its operation. The rest of the program is simply an encoding of the rules of the program which are outlined in the comments at the beginning of the program. The ANSI functions for random numbers. Although you can design the craps.cpp program by relying on the interface description, you cannot run the program until you have an implementation for the random number library. To make sense of that implementation, you first need to understand the facilities provided by the standard libraries for generating random numbers. The basic tools are already provided in the form of a small set of functions exported by the cstd-lib interface. Unfortunately, that interface is not well suited to the needs of the clients, largely because the results returned by the function differ from the machine to machine. One of the advantages of the random.h is that it provides clients with a machine dependent interface that is considerably easier to use than the underlying facilities on which it is based. The random.cpp implementation is based on a more primitive random number facility provided as part of the standard library interface cstd-lib. The function on which the implementation depends is called rand and has the following prototype: program to play a game of craps. So in the int main we have the randomize function at the top. Once we include any interface in our client program, we can easily use all the functions inside it without any dot notation or nothing. And we can easily just use the functions, which is good. Okay, it's understandable. Unlike most functions, rand returns a different result each time it is called. The result of the rand is guaranteed to be non-negative and no larger than the constant rand mix, which is also defined in as cstd-lib interface. Thus, each time rand is called, it returns a different integer between 0 and rand max inclusive. The value of the rand max depends on the computer system. When you write programs that work with random numbers, you should not make any assumptions about the precise value of rand max. Instead, your programs should be prepared to use whatever value of rand max the system defines. You can get a sense of how rand behaves on your own system by running the program const int n trials equals 10 int main, and then you just do like that. Okay, it's understandable. Although this number itself seemed rather arbitrary, it happens to be 2 raised to the power 31 minus 1, which is the largest number. This is just about the same function they have written. I don't think I need to read about it. But it's important to know what are they talking about the seed here. The initial value, the value that is used to get the entire process started, is called the seed for the random number generator. And where is the seed? The ANSI library implementation sets the initial seed to a constant value every time a program is started, which is why the library always generates the same sequence of values. To change the sequence, you need to set the seed to a different value, which is done by calling the function srand parenthesis seed. Srand function is essential to implementation of randomize, which resets the seed so that the sequence of the random numbers is different each time. The usual strategy is to use the value of the internal system clock as the initial seed. Because the time keeps changing, the random number sequence will change as well. You can retrieve the current value of the system clock by calling the function time, which is defined in the library interface ctime, and then converting the result to an integer. This technique allows you to write the following statement, which has the effect of initializing the pseudo-random number generator to some unpredictable point. So the randomized function is the same as srand parenthesis int parenthesis time parenthesis null. Why do we even need to do all of this? We can just use randomized function and it will just come up with a new value every time, and the pseudo random thing will become completely random, which is good. The random.cpp implementation. The ANSI functions described in the preceding section provides all the tools you need to implement the random.h interface. The implementation is contained in a separate source file called random.cpp. After the initial comment, the implementation file lists the include files it needs. The implementation needs C stdlib, C time, so that it has the access to the functions rand, srand, and the time. Finally, every implementation needs to include its own interface so that a compiler can check the prototypes against the actual definitions. The rest of the file consists of the functions exported by the interface along with any comments that would be useful to the programmers who may need to maintain this program in the future. Like all the other forms of expository writing, comments must be written with their audience in mind. When you write comments, you must put yourself in the role of the reader so that you can understand what information that reader will want to see. Comments in this .cpp file have a different audience than their counterparts in the .h file. The comments in the implementation are written for another implementer who may have to modify the implementation in some way. They therefore must explain how the implementation works and provides any details that later maintainers would want to know. Comments in the interface, on the other hand, are written for the client. A client should never have to read the comments inside the implementation. The comments in the interface should suffice. The use of the comments to explain the operation of the code are best illustrated by the random integer implementation, which converts a random number in the range 0 to the rand max into 1 that lies in the interval between the parameters low and high. As the comments indicate, the implementation uses the following four-step process. Okay. The four-step process. Where is the four-step process? We'll see. So the normalization, the first process. The first step in the process is to convert the integer result from the rand into a floating point number d in the half open interval 0 to 1. To do so, you all need to do is convert the result of rand to a double, then divide it by the number of the elements in the range. Then divide it by the number of elements in the range, because the rand max is often the largest integer the machine can hold. It is important to convert it into a double before adding the constant 1, which ensures that the division process a value that is strictly less than 1. Scaling. The second step consists of multiplying the value d by size of the desired range so that it spans the correct number of integers. Because the desired range includes both the endpoints low and high, the number of integers in the range is given by the expression high minus low plus 1. Truncation, as we know, it will remove everything after the fraction. Random integer with the lower bound of 0. Translation. The final step consists of adding the value low so that the range begins at the desired lower bound. The steps in this process are illustrated by the diagram, which shows how to call random integer 1,6 converts the result of the rand into an integer into the desired range of 1,6. Strings. In any programming language, strings are one of the most important data types because they come up so frequently in applications. Conceptually, a string is just a sequence of characters. For example, the string hello world is a sequence of 12 characters, including 10 characters, a comma, and a space. In C++, the string data type and its associated operations are defined in the string interface, and you must therefore include this interface in any source file that manipulates string data. In many ways, string is an ideal example of an abstract data type, which is the topic of the following chapter. However, given that strings are essential to too many applications and that they are more deeply integrated into the syntax of C++ than the classes described in chapter 4, it makes sense to introduce them before the others. In this chapter, you will look at the strings only from a client perspective, which means that you will be able to use them as a tool without having to understand how their underlying implementation. The data type string. In the chapter 1, you learned that the data type is defined by two properties, a domain and a set of operations. If you think about strings as a separate data type, the domain is easy. The domain is easy to identify. The domain of the type string is the set of all the sequences of the characters. The more interesting problem is to identify an appropriate set of operations. Early versions of C++ and its predecessor language C did not have much support for manipulating strings. The only facilities provided were fairly low level operations that required you to be very familiar with the precise representation of strings and work at a detailed level. The C++ standard introduction introduced the standard string type that presents an abstract view of string and a richer set of facilities for operating on strings. This allows us to focus on manipulating strings using their published interface without concern for how strings might be internally presented. Okay, there is a diagram. Steps required to calculate a random integer. Initial call to rand, normalization, scaling, truncation, translation. Who's gonna do that? Operations on the string type. So we make the string str equals hello. Then we add something to the string that's called concatenation plus. The addition operation has been overloaded or given multiple meanings. When plus is applied to numbers, it performs addition. When applied to strings, it performs string concatenation. It is an error to attempt to add two operands of incompatible type, such as double and a string. The shorthand plus equals form can be used to append onto an existing string. Both plus and plus equals allows concatenation of another string or a single character. As much as possible, operations on strings were defined so as to mimic the behavior of those operations on the built-in primitive types. For example, assigning one string variable to another copies the string contents. This assignment overrides any previous contents of the string 2 with a copy of the characters contained in string 1. The variables string 1 and string 2 remain independent. Changing the characters in the string 1 would not cause any changes to the string 2. It's different from the Python perspective actually, because if we assign one variable to another in Python, it's always going to be the two names of the same thing. If you change one, then you change another one. But in this, they're saying it's just making a copy. In Python, it doesn't make a copy if you assign something else to another variable. It's just two names of the same thing. So if you change one, it changes the other one in Python, but not here. It's not gonna change the other one. They remain independent of each other. When passing a string as a parameter, a copy is made. Oh, okay. Yeah, because a copy is not being made when we are talking about the structures. Okay. Hmm. This assignment overrides any okay, that's done. When passing a string as parameter, a copy is made just as with a primitive type. Changes to the parameter made within a function are not reflected in the calling function unless the string parameter is explicitly passed by reference. Two strings can be compared using the relational operators equal equals, not equals, less than, greater than, less than equals, greater than equals. Why am I saying all of these? These operators compare strings lexicographically, which follows the order given by the character codes. Basically, it's following the order of the ASCII table. This ordering means case is significant, so ABC is not equals to ABC in uppercase. If str equals to quit, you can retrieve the total number of characters obtained in a string by invoking the length function str.length. The syntax of calling the length function is different from what we have seen so far. If length were like the functions random.h, you would expect to call it like this. But it's a string method, so we do str.length parenthesis. So what makes length different is that it is an integral part of the string class and must therefore be applied to a particular string object. In the expression str.length, the object is this variable string. In the language of the object-oriented paradigm, this object to the left of the dot is called receiver, and the syntax is intended to emphasize that the object stored in the str is receiving a request to perform the length operation. Informally, it makes sense to think of this operation as sending a message to the object asking for its length and having it respond by providing the requested information. In C++, functions that are directed to a specific object were originally called member functions, but that designation is gradually giving away to the term method, which is more common in other object-oriented languages. Functions that are independent of an object, such as those you have seen up to now, are called free functions. Other than the use of dot notation to identify the receiver, the mechanics of calling a method and calling a free function are pretty much the same. It is possible to access the ith character from a string str using the notation like this. Same thing as Python. Str square brackets I. As with the arrays, index numbers in a string begin at 0. Thus, if str contains the string hello, then str0 has the value h. Yeah, I know that. The standard idiom for processing every character in the string looks like this, which I know. On each loop cycle, the selection expression stri refers to the ith character in the string because the purpose of the loop is to process every character. The loop continues until I reaches the length of the string. Thus, you can count the number of spaces in a string using the following function. Okay. As with the array selection, selecting a character position that is out of range for a string is not automatically recognized as an error. That will be typically lead to incorrect results. Oh. So that means if we have a string which contains hello and I'm trying to access str square brackets 25, it's not gonna give me error, it's gonna give me unexpected results which I want to see. So let's try doing that in a compiler. So what I'm gonna do is I'm gonna make a string str and then I'm gonna see out str square brackets 45. What does that do? Let's see. Why is it giving an error here if it says that it's not gonna give an error? Should I try 6? It's an error. The string interface exports a large number of methods, many of which come up only in relatively specialized applications. Table 3.1 lists several of the more useful methods. str.length parenthesis, it returns the number of characters. Str at pose or str square brackets pose, however it return the character at index pose. However, it used to access an invalid position at the map is where bracket has undefined behavior. We can also have a substring using dot substr function method. We put the position and the length. So we start from that position and we go till the specific length. Okay, we put the starting length and the starting position and the length till where we want to go. str.find will find a specific character starting from a specific position, I think. str.find pattern.pose, an overloaded version of the find that searches for a substring pattern instead of a single character. Oh, okay. st.insert pose comma text. This method copies the character from the txt and inserts them into the receiver string str starting at a position. Note this operation destructively modifies the receiver string. str.replace pause count txt. This method replaces the count characters starting at pause in the receiver string str with the entire contents of the string txt. Let's see how we can use all of these string methods. The principal function is Pig Latin, which converts an English word to Pig Latin by applying the following rules. If the word contains no vowels, no translation is done, which means that the translated word is the same as the original. If the word begins with a vowel, the function adds the string way to the end of the original word. Thus, the Pig Latin equivalent of alley is alleyway. If the word begins with a consonant, the function extracts the string of consonants up to the first vowel, moves that collection of the consonants to the end of the word, and adds the string ay. So trash will be ash, pray. Okay. The implementation of Pig Latin uses the substr function to extract pieces of the original word and string concatenation to reassemble them. Oh, this Pig Latin actually sounds really interesting. I want to see some examples of these. So apple will become apple, apple yay. Okay. And school will become ulskay. Glove will become ogle. Banana will become ananabe. Smile will become alsmay. String, ing string. Egg, egg ye. Eat, eat ye. Chair, air, chair. I was thinking that all of these new words will also make sense, but that's not the case. So we'll move to the implementation of it. So we have Pig Latin function in which we are giving a word as the input, and it will find the first vowel of that. If we don't find the first vowel, then we return the word as it is. If the first vowel index is 0, then we will add the way at the end of the word. Else we'll get the head by doing the substr function from 0 to vp and get the tail from the vp till the end, and then we will add the tail plus head plus ay, and that's it. Find first vowel is not gonna be hard. We'll just keep on searching. And is vowel should be a very easy function. The principal advantage of the string interface is that strings are treated as abstract values. When a function needs to return a string to its caller, it does so by returning a string as its value. Any operations on that string are performed using the operation exported by the library. The client is free from having to worry about the details of string representation and allocation. Even though this text relies extensively on the functions in the string interface, it is not necessary to understand that code from the implementation side. The whole point of the interfaces is that they protect clients from the complexity of the implementation. As you continue with the programming career, you will often make use of libraries even though you have no understanding of their implementation. So it is best to keep comfortable with that process as early you can. The struct the strutils.h interface. There are few minor convenience operations on strings that are used in this text as implement to the standard library. These functions are simple adaptations of the existing standard functionalities but packed in a way to be more convenient to use. This interface is called strutils.h. An aside about C style strings. So let's see how the strutils.h is written. Convert to lowercase, convert to uppercase, integer to string, string to integer, real to string, string to real. Wow. Arrays of characters with a sentinel value, the null character used to mark the end of the string. You can recognize older programs that operate on these C style strings by their use of the data type char, star, char, square brackets. Working on the C style strings is error prone because of the exposed pointer implementation and issues of allocation. Using the C++ string type frees the programmer from managing string storage and decreases the probability of difficult pointer bugs. Thus, you should use C++ strings wherever possible. That said, there are some facilities in the standard libraries that predate the introduction of the C++ string type and require the use of the older C style strings. You can obtain the C style equivalent from a C++ string using the method cstr. Where C++ string is expected, where needed, you can explicitly convert a string literal to a C++ string, a typecast like notation. Standard I/O and file streams. The most commonly used library is the I/O stream library. Every program in the text includes I/O stream. In order to display output using the cout stream, the I/O stream interface is extended in the fstream interface with additional features that make it possible to read and write files, which in turn enable you to store data values that persist even after your program completes its operations. Data files. Whenever you want to store information on the computer for longer than the running time of a program, the usual approach is to collect the data into a logically cohesive whole and store it on a permanent storage medium as a file. Ordinarily, a file is stored using magnetic or optical media, such as on a removable floppy disk, a compact disk, or a hard disk. The important point is that the permanent data objects you store on the computer Documents, games, executable programs, source code, and the like are all stored in the form of files. On most systems, files come in a variety of types. For example, in the programming domain, you work with source files, object files, and executable files, each of which has a distinct representation. When you use a file to store data for use by a program, that file usually consists of text and is therefore called a text file. You can think of a text file as a sequence of characters stored in a permanent medium identified by a file name. The name of the file and the characters it contains have the same relationship as the name of the file and as the name of the variable and its contents. As an example, the following text file contains the first stanza of Lewis Carroll nonsense poem Jabberwocky, which appears in Through the Looking Glass. When you look at a file, it is often convenient to regard it as a two-dimensional structure, a sequence of lines composed of individual characters. Internally, however, text files are represented as a one-dimensional sequence of characters. In addition to printing characters, you can see files also contain the new line characters, which marks the end of the line. The file system also keeps tracks of the length of the files, so programs that reads files can recognize where the file ends. In many respects, text files are similar to the strings. Each consists of an ordered collection of characters with a specified endpoint. On the other hand, strings and files differ in several important respects. The most important difference is the permanence of the data. A string is stored temporarily in the computer's memory during the time that a program runs. A file is stored permanently on a long term storage device until it is explicitly deleted. There is also a difference in the way you use data in strings and files. The individual characters in a string may be accessed in any order by specifying the appropriate index. The characters in a text file are usually accessed in a sequential fashion, with the program starting at the beginning of the file and either reading or writing characters from the start to the end in the order. Using file streams in C++. To read or write a file as a part of the C++ program, you must use the following steps. Declare a stream variable. The fstream interface exports two types: ifstream for files being read from and the offstream for files being written to. Each type keeps track of the information the system needs to manage file processing activity. Thus, if you are writing a program that reads an input file and creates a second file for output, you need to declare two variables as follows. Open the file. Before you can use a stream variable, you need to establish an association between that variable and an actual file. This operation is called opening the file and is performed by calling the stream method open. Like the method seen previously on string, you invoke it using dot notation on the string. For example, if you wanted to read the text of the jabberwocky.txt, you would execute the statement in file.open jabberwocky.txt. One minor glitch is to note is that the open method expects a C-style string as the argument. A string literal is acceptable as is, but if you have the file name in a C++ string variable, you will need to pass it as a C-style equivalent. Oh, okay. If a requested input file is missing, the open operation will fail. You can test the current state of a stream by using the fail method. As a programmer, you have responsibility to check for this error and report it to the user. If the infile.fail error could not open file. In some cases, you may want to recover from such an input file failure. For example, if the user accidentally typed a non-existing file name and tried to open the input stream once again. In such cases, you must first clear the fail state, then that the input stream variable will be in after such a failure. You can do this by calling the clear method on the stream as exemplified below in file.clear. Transfer the data. Once you have opened the data files, then you use the appropriate stream operations to perform the actual I operations. For an input file, these operations read data from the file into your program. For an output file, the operations transfer data from the program to the file. To perform the actual transfers, you can choose any of the several stages depending on the application. At the simplest level, you can read or write files characters by characters. In some cases, however, it is more convenient to process files line by line. At a still higher level, you can choose to read and write formatted data. Doing so allows you to intermix numeric data. I need to stop.